So first of all these different, we're starting off a little, different components. These are electrical and electronic devices. So can y'all identify these? These over here, nothing but what? Switches. This is a relay. Everybody know what a relay is? You okay there? Guess no. These are vacuum tubes. Vacuum tubes were our first so basically, we started, light switches have been around for centuries. Ever since basically electricity has been there, they realized they needed to have a way of turning the current on and turning the current off. Then they needed to, so switches used to be huge. Then they realized that they could use a device called a relay to not only control a lot of current, but also not even use the same voltage. So I could energize the relay with 5 volts, but it could control 120 volts, right? You understand that? Or I can have the little ignition on my car turn a starter. And so the starter is not turned on by your ignition switch. Your ignition switch energizes a starter relay, and the starter relay provides all that current to that starter, right? You understand? So relays have been around for a long, long time. Eventually they realized that but they can change the level, right, of voltage, so you can have 120 volts on the contacts and have the coil at 12 volts, but we couldn't have a varying gain. We couldn't vary the gain. Y'all understand that? So they came along with devices called vacuum tubes. And vacuum tubes control electronics. It controls electrical current using an electrostatic field, which are really, really neat. But what we could do with this is we could dynamically control the flow of current. So these guys act like a big old rheostat, but instead of you turning the rheostat knob, we control the resistance of the tube electronically. But we do it with an electrostatic field. But these guys here required a lot of voltage. They ran off a lot of heat. They needed to generate heat to generate an electron cloud. These things used to run on about a 250 volt supply, which made them very dangerous. We had to heat them up so they consumed energy when they were just sitting there. So eventually they moved into solid state devices when they invented a device called a transistor. A transistor, basically they control bipolar transistors, which are the first that we get into. Those control electrical current with a real small current, which is pretty neat. And then we get into what they call field effect transistors that operate a lot like a vacuum tube, but we don't have to operate them at the real high voltage. Eventually they realized, of course, a lot of the circuit, especially in computers, a lot of the things are decision making. They don't have to have a lot of current drive. What depends on the size of these vacuum tubes and the size of these transistors or how much current they need to control. So the more current they need to control, the bigger they have to be, right? You understand? In computers, we're dealing with ones and zeros. We either put a voltage there or we don't have a voltage. We call them highs and lows. They don't have to drive a lot of current, so that means the transistors can be extremely small. Okay, y'all understand that? Eventually, they had the ability to integrate multiple transistors on a single piece of silicon. And these became known as integrated circuits. And now we're into thousands of transistors, well, actually millions of transistors on a single wafer on our current microprocessors. But these guys right here have one thing in common. They operate on what current? They operate on DC. Relays can operate, we can get relays that operate on AC or DC. We can get relays that we switch the contacts with DC and we control AC. But your solid state devices operate off of DC. But the problem is, a big majority of them actually, even though this computer's got batteries in it, we have to charge the batteries, right? And this guy on this side, this is what? This is AC, right? You understand? On this side, this is what? This is DC. and it's well controlled DC. We're going to look at what we call regulated, unregulated power supplies. So to understand electronic power supplies, we're going to have to understand some AC. We're going to have to understand that. So solid state electronics, semiconductors are solid substances, usually silicon or germanium. We're seeing less germanium as we move through. Silicon has better temperature characteristics, so it has the ability to operate at a bigger range. All the devices that we're going to deal with here is going to use a silicon substrate. Silicon substrate. Silicon is basically glass. This has a conductive between, so we call these semiconductors because they have a conductivity between an insulator and a conductor. And we'll look at that when we get into this. And we do strange things with this where we can actually change the conduction. We call it doping, where we literally change the characteristics of the semiconductor. Doping is the process of adding a small percentage of a foreign atom into the semiconductor that allows electronic control in its conduction characteristics. So we have a semiconductor which is neither an insulator and it's not a conductor. We introduce another atom into that and we can literally start controlling the conduction characteristic of this thing. So we can vary the resistance of this thing dynamically, which is pretty neat. Solid state refers to electronic components, devices, and systems based entirely on doped semiconductors. And solid state devices operate on what? DC. But we don't want to have these batteries all over the place. All batteries run down, right? You understand that. We want a power source that's there all the time. So your cell phone operates off DC, but we use batteries. But those batteries do what? They run down. So we plug it into AC to charge them up. Now, unless you got one of those little DC charging modules. But even those you have to charge with an AC charger. So DC flows in one direction. The electrons in the DC circuit flow from negative terminal of the voltage source through the circuit back to the positive terminal of the voltage source. The voltage source never changes polarity, and this guy is very easy to electronically control. So if you got anything that's electronics, it runs off DC. Even if it plugs into the wall, it runs off DC, right? You understand that? So somewhere in that TV, somewhere in this computer, these guys are obvious because they're out here, most laptops and desktops and cell phones. The DC power supply is external. The power supplies on these are inside the computer, right? You understand that? So your TV has a power supply in it. That's not true. A lot of your flat screen TVs now have one of these. You'll have the external power supply and you'll plug it in almost like you do your computer. Produced by DC generators, batteries, produced by thermocouples. These guys produce DC with heat. Solar cells. Everybody see these solar cells all over the place, right? Solar cells. Piezoelectric devices. If you're a smoker or if you got an electric cigarette lighter, if you got a cigarette lighter that you pop, you're looking at the piezoelectric effect. You know, the old cigarette lighters used a flint and then a wheel that you spun the flint. And basically, you know, you can go to Harbor Freight and buy these flint starters for a fire. Most of your cigarette lighters don't do that now. You hit a little old button, you hear a pop. What it's doing is hitting a piezoelectric crystal, and that piezoelectric crystal generates a voltage that's high enough to do what? To generate a spark. Electronically, AC to DC converters. And this is what these guys are. These are AC to DC converters. We call them power supply. And bioelectric. You know, lightning bugs produce, we are bioelectric. We produce electricity. We operate off electricity. If you ever watch The Matrix, everybody seen The Matrix? They use us as what? They use us as batteries. They use us to run all the robots. So we are bioelectric devices. We produce electricity. Our brain works off electricity. Our sensors take physical and converts it over to electricity and transfers it to our brain, and our brain processes electricity. Y'all knew that, right? That's why we can set stuff off. Yeah, that's why we have touch screens. Touch screens worth we have different types of touch screens. We have some that works off pressure. So if you got something where you can take just about anything and push on it and make it works off pressure. The rest of them work off capacity, which basically picks up our electrical impulses coming off our finger. I can show you this on the oscilloscope. I can show you me. I'll show you all that later. In fact, I don't think I got. Oscilloscope has a really high input impedance, so it doesn't load down signals a lot like your meter does. So normally what we can do is we can literally touch the end of a scope probe as soon as it pops up. Hopefully it's connected. Okay, so this is an oscilloscope. This is me. That's Alabama Power, so this is me. All I'm doing is what? Touching it. So if I've got this available to me all the time, then we can set up a screen so we can use that to figure out where my finger is on the screen somewhere, right? So a lot of your touch screens, especially on your cell phones, operate off of this effect right here. That's it. Y'all can touch it too. Of course, I got the scope turned down to 50 millivolts per division, so but it's still picking up pretty good. And so that's how, you know, you go to the doctor and they want to monitor your heart. They put these little plastic pads, and that's nothing but this like a scope, and they put them on you, and it's picking up these electrical impulses. Right? Come on, guys. Here we go. So here's some devices, batteries. Car batteries we're all familiar with, DC generators, solar cells, we've all seen those. You see them all on the side of the free interstate, right? So a lot of calculators have solar cells in them. You don't have to put batteries in them anymore. Piezoelectric, you have these lighters that you see that effect all the time. This is one that we have these around the house. My wife likes candles in the house. And then, of course, devices called thermocouples. We use these guys. We use the voltage that these guys produce to actually measure temperature, because the temperature they put out, the voltage they put out is proportional to the temperature that you're trying to measure. Solid state devices operate off DC. The power grid is what? AC. Function of the first solid state devices was to convert what? AC to DC. First devices, the first vacuum tube they came out with was what they call a diode tube. And it converted what? AC to DC. But to understand how these devices work, one must have a basic understanding of alternating current. Are we okay? So these are some terms we'll have. Cycle, frequency, period, alternation, RMS, peak, 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 DC average. And components we'll look at, in this class we'll look at the AC voltage source, inductors and capacitors, and of course transformers. Are we okay? Everybody okay? So alternating current constantly swaps the direction. Now, there's a lot of things that can be AC, but they're not the way we generate power. So what we're doing is we're looking at how this AC that we use as a power, how is that thing generated? How's that generated? Everybody understand? And I can put all types of signals up here on my oscilloscope that would be considered to be AC, but they're not the AC that we use to generate power. So this is a function generator. And what's nice about a function generator is it takes AC, converts it to DC, and then once we got it in DC, we can do what? We can control it. So they can regenerate AC. So this is why you can go out and buy these inverters for your car. You can plug them into your, so my wife's got a 120 volt her van, she's got a 120 volt plug in her van. Well, how does it get 120 volts AC? Well, it does it electronically, right? You understand? There's an inverter in there that electronically takes DC and reconverts it back into what? AC. So what's nice about this guy, this is a function generator, and that's its function in life, is to generate signals. And what it does is it takes AC, converts it to DC, and then we can generate different types of signals with it. So this is not Alabama Power, this guy's doing it electronically. So this is the way Alabama Power generates AC. So this line right here, you can see this real bright line right here, that's 0 volts right there. So in this time, then it's generating a positive voltage and current will be flowing negative to positive. Here it generates a negative voltage and it still be flowing, but now it does what? It literally switches direction. And this is AC. This is the way Alabama Power. So if I was to take this oscilloscope and look down at that power plug out there, this is what it would show. Except it would be a lot more. This would be. So what I can do here is I can change the amplitude. Oops, sorry. I can change the amplitude real easy if I want to. And then I can change something called the frequency. This is AC. This is AC. Why is it AC? Because this is still positive, this is still negative, right? You understand? So it's AC. The current would be doing what? Would be changing direction. But this is not what Alabama Power generates. So we're not going to worry about this. This is AC. But this is not what Alabama Power generates. This guy here, notice it's not that nice little old smooth waveform that we saw before. This is not what Alabama Power generates. This is the kind of stuff you have to understand in AC. We don't have to understand this. What we need to do is understand what? In this class, what we need to do is understand this guy right here. See it? Nice and pretty waveform. Crosses 0. So notice on AC, how much work do I have right here? V is equal to 0 volts. I is equal to V over R, Z divided by R, 0 divided by, so we get no work at this point right here, right? You understand that? So we get no work here, we get no work there, we get maximum work right here, and then it varies, and then it drops down to negative. How much work we get there? We get exactly the same work, but the current is flowing in the opposite direction. And this is AC. This is the way Alabama Power generates power. This is what we're going to have to take and convert to DC right here. This waveform right here. Are you okay? But there's a lot of different ACs. So when we talk about AC, there's a lot of things we can do. I forgot this one too. This is called a triangle waveform for obvious reasons. Because it looks like a what? A triangle. This is called a sawtooth waveform. Because it looks like a what? A sawtooth. This is called a pulse waveform. Oops, I turned it off. This is called a pulse waveform. By the way, my scope is not set up right. It actually don't have this thing right here. Oscilloscopes. I'm gonna switch this over. Oops. What did I just do? I've never seen that. I don't know where that came from. I need to figure out. I don't have time right now. I pressed that button. Okay. This is actually what's there. So see, it's nice and flat across the top. We call this a pulse waveform. A lot of people call it a square wave. But this is still what? Still AC, right? So there's the basic waveforms of AC. We have what we call a square wave. Then we have what we call a triangle wave. This guy. We have what we call a sawtooth waveform, which is a variation. I don't know what it's a variation of that. And then we have this waveform right here, which we refer to as a sine wave. Which we'll look at in. Are we okay? Now all we have to do is worry about the sine wave. So what we're going to be doing is taking Alabama power and convert it over. This is what's nice about an oscilloscope, folks. A meter averages everything. An oscilloscope shows you what's there. So this is exactly what's there. If I looked at this as a meter, the meter's going to average this out, right? You understand that? And we'll talk about that in a minute. So AC, the voltage source of an AC circuit constantly swaps polarities, which causes the current to do what? Constantly swap polarity. Everybody okay? It's less expensive to generate. So your car operates off DC, but your generator is not a DC generator; it's an AC generator. They call it an alternator. Why? Because it's cheaper and easier to generate. And then we have the ability to take that AC, and convert it to what? DC, to charge your battery and to run your radios and all that neat kind of stuff in your car. But AC is a lot cheaper to generate. DC generator is very expensive per kilowatt over an AC generator. And there are more to them. DC generators require more maintenance. They have a thing called a commutator on it. So you gotta do more maintenance on a DC generator. Even though your AC generator has some maintenance, DC generators would have a lot. Extremely efficient to transmit, and we'll look at that in a minute. Voltage levels can easily be changed with what? Devices called transformers. AC motors are less expensive per horsepower. They're harder to control, but they're a lot less expensive. So that's why you probably don't have any DC motors in your house. Well, that's not true. Your DVD player, the motor that spins that disc in there is DC. And your car, all the motors in your car are what? DC. Produced by AC generators electronically or bioelectric. When I started dealing with this, I didn't know that, but electric eels produce AC. They produce two voltages. They produce a real high voltage and a low voltage, but one of them is AC, which is pretty neat. Everybody knows their alternator, right? I've seen that guy before. It's under the hood out there. AC generators. Anybody got one of those? I went out and bought one of these after the snowstorm of '93 when we got 13 inches of snow and we was without power. Some people were out power for a long time. I was out power for about a week. So I went out and bought me a big generator. How many times have I used it since then? Never. I crank it up to make sure it's still okay. But I've never had to use it. I guess that's why, because I bought one. Power plants. Alabama Power uses AC generators, right? Bioelectric. Electric eels produce, so they kill with DC. They can produce about 870 volts DC, and then they stun with AC. So if they're going to stun something, they get them with AC, and then electric eels are neat. Inverters, DC to AC inverters. Some of y'all might have some of these at your house. You can buy these at AutoZone, or you can buy them at Harbor Freight. You know, you can buy them at Sears. You can buy them just about any place that's got an auto place. You can buy these inverters. And then, of course, function generators, which is what I have here, which we'll use a lot in this class. We'll use a lot. Are we okay? This is a symbol for an AC voltage source. So the symbol for a DC voltage source, a lot of people say a battery, but that is the symbol of a DC voltage source. We go between dash lines and long lines, right? Normally they used to, each one of them would represent a cell. A lot of people don't understand we call them batteries, but a AAA is not a battery, it is a cell. But we use them in combination to create batteries, right? You understand? It's just that everybody called them batteries because of the batteries in cars. So now they're commercially known as batteries, but they're not batteries, they are voltage cells. Because a battery means more than one, right? You understand? The only battery that we have, of course, car batteries, those are true batteries. They have 6 cells inside of them. And then 9-volt batteries have cells. They have 6. Huh? That is a cell. They call them cells because that's what they were. But the problem is, when automobiles started coming out and we started calling that big D thing out there a battery, everybody started calling them batteries. So they commercially call them batteries. So a lot of things we have commercially is because of the commercial market, you know. So like these little things we have in our pocket, those are these guys. Electrically erasable, programmable, read-only memory. But people don't say that, so we call them thumb drives, we call them flash drives, we give them all different, and that's what they're commercially known as. But basically, they're double EEPROMs. So things change. Alternating current is provided by voltage sources whose polarity changes direction. But we're talking about not AC current. I need to read AC power is generated. But it changes directions at a constant rate. So that rate of this AC is constant because this scope is not showing me the same thing, but it's the same every time, right? You understand? It's just like movies. A lot of people don't understand movies. Movies are a bunch of pictures. And they flash those pictures by in a rate that we can't see. Our eyes just sum them together. We call them frames. They shoot those pictures up there. If the pictures don't change, everything looks to be stationary. So if the pictures are exactly the same, then even though they're throwing multiple pictures up there, it doesn't move. So this is what all these guys are exactly the same. And if we can synchronize our scope to one of them, then it makes it appear like they're stationary, right? You understand? But they're not. These guys are occurring at 127 times a second for a cycle. So it's changing that almost at 260 times a second. It's actually changing from positive to negative 260 times a second. But it's exactly the same every time. So if we can synchronize our oscilloscope to one of them, then after that, what it draws is going to appear to be the same thing, but it's not. It's actually different cycles. Okay, y'all understand that? Yes or no? No, it's moving because it's a digital oscilloscope. You're talking about right in here. This is a digital oscilloscope. So what this thing is literally doing is taking an AC signal and converting it and running it into an analog to digital converter. And you can't hardly see it. I don't know if I can show you up here. It's actually done in steps. If I had an analog oscilloscope, this guy here would be just as smooth as it could be. It's the digital oscilloscope that creates that right here. If we don't synchronize the scope, we call it a trigger. So this is the trigger. If we don't synchronize it, then we're not it's still doing exactly the same thing, but my oscilloscope is not synchronized with the signal. So what we do is we have something called a trigger. A trigger, and what's nice about this scope, it shows you the trigger. And so when I get that trigger down into the waveform, now it's synchronizing on that. And by the way, this is the trigger point, but notice the waveform starts right there where I put that trigger. You understand that? Yes or no? And notice if I move the trigger down, this one shifts to that point right there. So what I've done now is I've referenced my scope to the waveform. So my scope doesn't display the picture until it hits that point on that waveform, and then it shows the picture. Well, if every one of them is identical and I started at that point every time, then to us it looks like it's stationary, right? You understand that, but it's not. We're synchronized. We're synchronized with it. So this is why your monitors and your TV has to be synchronized with the camera. So if you understand video, what they send, what the station sends, every time it sends a new picture, it sends out a sync pulse. So now your TV is in sync with the camera or the video, right? And now your picture appears to be stationary. If you got a real old TV, it had what we call horizontal and vertical hold that you'd have to adjust to make it synchronized. If you didn't, it would either roll this way or lay down on its side. So this repetition produces a waveform shown on the next slide, but we've already looked at it, right? An AC waveform is referred to as a sine wave because its amplitude varies with the trigonometric sign of the voltage and the current and the power. We'll look at that in a second. So so we generate AC on a circle. This is a real neat animated GIF. So you can see as it moves around. And what we're doing is we're dropping a vertical. So notice this line right here. Y'all see that? And notice we're always forming a right triangle. Can y'all see that? Y'all know what a right triangle is? It's one, what's the sum of the angles of any triangle? No, the sum of all the angles. 180 degrees. Right triangles, one of those angles is 90 degrees. So what that means is the other two has to be 80 degrees. I mean, they have to sum up to, 90 degrees also, right? You understand that? So the ratio of the sides have to be perfect on right triangles. So if you know any one angle, then the other angles have to be the same relative size, right? You understand what I'm saying? To get that angle. So this is moving around in a 360 degrees. And notice what we're doing is we're taking this point right here and we're transposing it over here. And what does it create? It creates this waveform called a sine wave. So it's not linear. Linear means it moves in straight lines. So my triangle wave would be linear AC, right? You understand that? It's not linear, which means the voltage at this point does not change at the same rate. It doesn't change at the same rate. So what happens is it starts off and as it moves on, the rate that it changes starts going down until it gets up to the very top, and then it don't change anymore until it starts dropping down on the other side. Notice that one complete cycle of the waveform is generated. So this is the way it's generated. It's generated on a circle. We have 360 degrees in a circle. So what we do on AC is we reference positions on the waveform as degrees. So one waveform, one complete waveform would be equal to what? 360 degrees. It would cross right here at 180. It would cross right here at 360. 360 of one waveform is 0 of the next. So you have to picture it on AC. You have to picture it like 12 midnight. What's 12 midnight? It's the end of one day, but it's what? It's the beginning of the next. So 360 degrees and 0 degrees are the same. 360 degrees would be the end of this waveform. 360 degrees for this waveform would be 0 degrees for the next one, right? You understand what we're saying? Just like midnight. If you understand midnight. But what I want you to do is as this thing moves around and it's not at 0, so this is 0. So this would be 0 degrees. This would be 180 degrees. And what happens at 180 degrees? It crosses what? It crosses 0. This would be 90 degrees. At 90 degrees, we hit the peak value, the positive peak value, right? You understand that? At 270 degrees, we hit the negative peak value, right? You understand that? So we reference an AC waveform in degrees. Does that make sense? Because it's generated on what? It's generated on a circle. But what I want you to see, 90 degrees, we don't have a right triangle. 270 degrees, we don't have a right triangle. At 0, we don't have a right triangle. At 180, we don't have a right triangle. But any angle between those, this thing creates a right triangle. Y'all see what I'm talking about? And of course, if we know that right triangle, then we can solve for this value right here. If we know this angle right here, then we can solve for that angle right there. And we use the sine function. So since we can solve for the instantaneous voltage. So you can take the sine of 45 degrees, and you could multiply that times the peak value, and that would tell you what voltage it would be at 45 degrees, which would be 70.7%. A lot of people say, well, if 90 degrees is maximum, and this right here is 0, what would the volt, and this is 10 volts, what would it be at 45 degrees? A lot of people would say 4.5 volts, but it's not linear, right? You understand that? It starts off almost like this, and then as it approaches peak, it starts doing what? Levels off. So 50% actually occurs at sine occurs at 30 degrees. So if you take the sine of 30 degrees, y'all got your calculator? Take the sine of 30 degrees, it's 0.5. So if this is peak voltage right here, and then I say, okay, what would it be at 30 degrees? You'd say peak voltage times 0.5. That's going to give you half a peak. If you took the sine of 45 degrees, it's going to be 0.707. So that's 70.7%. So, and this is why it's called a sine wave, because the voltage varies with the sine of that angle, right? You understand what we're saying? So you can figure out the instantaneous voltage. We can say, okay, what value is it as 180 degrees? Well, if you look at a minus 180 degrees, it's going to be a minus 1. So if you had 10 volts peak, this is going to be a plus 1. So if you had 10 volts peak and multiplied it by the sine of 90 degrees, it's going to be 1. So that's going to be 10 times 1, so it's going to be 10 volts, right? You understand? If the peak value was minus 10 volts, if you multiplied that by, it'd come up if you took 10 volts peak and multiplied it times minus 1, it's going to say it's going to be a minus 10 volts. So it means the voltage on the output of a sine wave varies with the sine of that electrical angle. So that's why it's called a what? That's why it's called a sine wave. But it's not, all AC signals are not sine waves. Everybody understand that? And we looked at that a while ago. 0 volts are generated every time it crosses the horizontal axis. So this will occur at 0 degrees and 180 degrees, right? Understand that. The peak voltage, V peak, we call this the peak voltage right here, is generated every time the radius crosses the vertical axis. So we call this positive peak and we call it minus peak. But they're exactly the same value, except they're going to be opposite from each other. So it's a mirror image. So if my positive peak is 10 volts, my negative peak is going to be what? Minus 10 volts. That makes sense. So this is some terms. So these waveforms repeat, and they repeat at a constant rate. One repetition we call a what? Cycle. Everybody understand that? So one repetition of a repetitive waveform, we call it a cycle. Everybody okay there? Any questions? So this would be a cycle. This would be another cycle. And what goes on, these things goes on. How long do they go on? Well, they go on as long as Alabama Power is generating power. Sometimes we lose power, right? We have what we call blackouts. That's when the sine waves are not occurring. An alternation, this is an alternation right here. So we call this the positive alternation. So what do we call this one down here? Yeah, we call this the negative alternation. These guys here occur at a precise rate. We call that frequency. So Alabama Power generates 60 cycles per second. That's Alabama Power. So frequency is the rate of the cycle. Everybody understand that? Everybody okay there? Any questions there? So this is when I look at my function generator. By the way, this is not only a function generator, it's also a frequency counter. This gives me the frequency. So right now we're running, it's 129 cycles per second. And what's nice about this, it's electronically generated. I can't change Alabama's Power's frequency, right? You understand that? Who determines that frequency? Alabama Power determines that, right? And they can't change that, by the way. It's very, very critical, and we'll learn a little bit about that as we go along. But I can, since this is electronically generated, I can change the frequency. This guy, in fact, will go all the way up to 20 megahertz. 21.9, I'm sorry, this would be 21, no, this is megahertz. 21.987 megahertz. So we can't do this without Alabama Power, but since this is electronically generated, not only can I change the frequency, I can also change the amplitude of that frequency. Everybody okay? What's this piece of test equipment? This is called a function generator. But it's actually two. It's a function generator, and it's also a frequency counter. So not only does it generate the signal, it tells us what frequency it is. And we'll show you how to measure that with an oscilloscope. The period is the what? The time it takes per cycle. So what happens when frequency goes up? What happens to the period? It what? Go down because they're opposite of each other. So if the period is the time it takes per cycle, if your frequency goes up, you're getting more cycles per second, so the period has to go down. And they're directly proportional to each other. So if I double, they're inversely proportional, excuse me. If I double the frequency, the period halves. If I half the frequency, the period doubles. Alabama Power's period would be what? So if I'm doing 60 cycles in 1 second, how long would 1 cycle last? 60 cycles in 1 second. How long would 1 cycle? What would the period be? 1/60th of a second. Right? You understand that? Now, of course, what we usually do, normally here we don't deal with fractions. We deal with decimals, right? You understand? Which is 16.666 or 16.7 milliseconds. I did that in my head, right? Y'all believe that? Now, I've been dealing with Alabama Power so long, this is something that I know. So one alternation would be 8.33 milliseconds. It's actually 16.666666666, and it goes on forever. So this is the rate. So we get a new cycle every 16.77 milliseconds. So AC does not have a polarity. Y'all understand that? Why? Because it's constantly what? Changing. Right? You understand that? 60 times a second. This alternation right here would only last 8.3 milliseconds. How long would it be at peak right there? That's something we just can't even understand. It's only there for no time, right? You understand? Before it swaps and heads back down. So how much work am I going to get out of this? Well, I'm not going to get peak. And I'm not going to get peak. So we call this peak for obvious reasons. We call this right here peak to peak. So my scope measures peak to peak voltage. Are you okay? Lost anybody yet? So what is the period? The period is the time. The frequency is the rate. All right? You need to understand that. A lot of people get those two confused. If period goes up, frequency is going down. If the period goes down, frequency is going up. Those things, guys, are inversely proportional. Anything that's inversely proportional, we can use what we call the reciprocal. In fact, we do this so much to figure out something, the inverse of a number. So an inverse is the opposite of, right? You understand? We do this so much that Scientific Calculators has a reciprocal key on it. It's either going to be 1 over x or it's going to be x to the minus 1. Both those are, if we raise any number to the minus 1, that takes the reciprocal of the number. So on your scientific calculator, your reciprocal key is going to be one of those. It's going to be either it's going to be 1 over x, or it's going to be what? X to the minus 1. Both those will take the reciprocal. And to figure out how much DC we get from the AC, we're going to have to deal with the period. So this is what we're talking about. Here's the angle. We call this the angle theta. And if you take the sine of the angle theta and multiply that times V peak, the positive peak, it will tell you the instantaneous voltage. So that's why it's called a sine wave. Everybody okay? Yes or no? Because the voltage varies with the trigonometric sign of the angle. The angle created at the radius of the horizontal axis is called the angle theta. And this shows you some basically, and notice this is where the angle, so any point on this, if I drop a vertical from that, which represents that voltage right there, then what type of triangle does this create? It creates a right triangle. This right here, the hypotenuse, is always equal to VP. Y'all understand that? So what I can do is, if I know this angle, I can multiply that times this by the radius right here, and it will tell me the length of that side right there. And that's what it works. And this is a little trig, but we don't need to know that in this class. All we need to understand is why it's called a watt. Sine wave. When you get into AC, you'll learn more about this, because you'll deal with that with a lot. The average, this is very important too for this class. The half cycle average of an alternation is, and I don't like this. Why I don't like it is they throw a number out there. Since we deal with a circle, we learn something, but we don't understand what it is this guy right here called what? Called pi. What is pi? What is pi? It has nothing to do with a triangle. It's a circle. What is pi? How is pi calculated? No, what is pi? The pi is the circumference. So this is the circumference right here. So if I measured this right here, this would be what we call the circumference. We call this the what? The diameter. If you take the circumference of a circle, any circle, and you divide that by the diameter, it will always equal pi. So pi is the circumference divided by the diameter. That's what it is. So every circle has this exact ratio between the diameter and the circumference. And it is an unreal number. It is constant. It never repeats, right? You understand? And how long does pi go on? How big is pi? Nobody knows. It hasn't started repeating yet. Last time I checked, they calculated it to the 2 billion digits. There's a site on the internet, pi site, where they got it calculated down to 1 million digits. It goes from page to page to page where they've gone 1 million digits. So pi, so we got to quit somewhere. So what do we usually use for pi? We usually use 3.14. There was some kid on that, one of those shows, one Steve Harvey does with little kids that could quote pi down to, I forgot, like 100 digits. I used to like the person of interest, and some of y'all in my classes probably heard me tell you this, but he brought up a point. He said every number that has ever been written is in pi somewhere. So your Social Security number is in pi somewhere. It's in consecutive digits. So it's really, really neat. So pi is really, really interesting. Well, since AC is generated on a cycle, then we can use this pi to calculate a bunch of stuff when we start dealing with this outside of this circle right here, right? So when you get into AC, a lot of your formulas deal with what? With pi, 3.14. For 2 pi, we use 6.28. And by the way, if you use it on your calculator goes out to like 13 digits, and it's a lot higher resolution than we would ever need. So usually by the time you hit the pi key on your calculator, you could already punched in what? 3.14 or 6.28. So this is the average value. So when I deal with this out here, we're dealing with the circumference of the circle. Everybody understand that? So this average right here is actually equal to the average. This is the formula right here. It's equal to 2 VP divided by pi. Now, if you split this off and said, okay, I'm going to come over here and put V peak over here and put 2 pi right there, then I could come up here and say what? 2 divided by pi would always be equal to what? 0.637. So that's where the 0.637 comes from. To me, it's a lot easier to keep up with 2 V peak over pi than try to keep up with this 0.637. Because I know it's generated on a circle. All your AC formulas deal with pi. So 2 V peak over pi is going to be 6.37. If we multiply that by V peak, that will give us the average value of an alternation. The DC average of an alternation. What's the DC average of a cycle? What's the DC average of a cycle? I'm going to take my meter, and the stand's messing off of it. Let's see if I got something I can prop it up. I'm going to turn it on. And I'm going to take these meter leads, and I'm going to put it into my power strip over here. And I'm going to put it on AC. And 200 volts. And I'm going to come up here and plug my meter into my power outlet. And it's measuring what? Can y'all read that? So we have 112.5 volts AC. What's it going to measure when I switch my meter to DC? What does it measure? 0. What does it measure when I put it on AC? Well, there is not 0 volts there, right? You understand? This gets a lot of people hurt. So what you're doing when you put it on DC, it's giving you the DC average of a cycle. So I'll have a positive 0.637, a negative 0.6367. You average those two together, and you come up and get what? 0. So the average DC value of a cycle is what? 0. Would it kill me? Yes. So this is very important on your meter, if you, especially a meter like this, because all it does is take a little button right there, and now it measures 0, and I don't look up here and see this DC up there, and I think there's no voltage in the circuit, and I stick my hands in there and I get my butt shocked, right? You understand that? So what's the average DC value of a cycle? 0. So we got to come up, but in AC, the negative alternation does just as much work as the positive alternation. So there is not 0 volts there. There's 0 DC, right? You understand that? But there's a lot of AC. Now follow this so far. Let's take a break. 10 minutes. I give you formulas, but not the entire sheet. That makes sense? And I do that on purpose because what I do on the test is I give you the formulas that you need for that test, and that way you're not looking at formulas that you don't need. So what you get on the test, they're the same formulas, but I give you a partial of the sheet. Does that make sense? So when we're dealing power supplies, I only give you the formulas for power supplies. But that's yours. And that's the last copy that I'll give you of the full phone sheet. Because if you lose it, where can you get a copy of it? On black. You understand that? Well, it depends if you got a color printer or not. I got a color laser. Everybody else, so what's the average value of an alternation? 63.7 2 V peak over 5. Y'all understand that? Yes or no? That's what I remember. And that just flows off your tongue, and that way you don't have to remember 0.637. And later on, when we start adding to that or subtracting to that, then y'all understand that? So we looked at other types of waveforms. I showed y'all triangle wave. What's nice about a sine wave is that a sine wave varies at such a precise rate. It's not linear, but we can't calculate it using an average. Because if I was to come over here and average this out, then if this was positive 1, then what would happen is this negative 1 would cancel that out in an average, right? You understand? This positive 2, I have a negative 2. This positive 3.96347, I have a negative 3.567, right? You understand that? So this is why your meter, when it gives you the DC average, it averages it. So we got to come up with another method to figure out what we don't call it the average voltage, we call it the effective voltage. Now what the effective voltage is, if I take this AC and I put it across a resistor, it's going to give us work. Because we put current, even though the current is changing, it's still current. If you put current through a resistor, you get work, right? You understand? When you talk about Watt's law, there's no such thing as a negative wattage, right? All your wattage is wattage. So 100 watts is 100 watts. There's no such thing as a negative 100 watts. Everybody understand that? So negative current flow produces the exact same power as positive if the current flow is the same. Y'all understand that? So they had to come up with a method to calculate this effective voltage. So anytime we square a number, if we square a number, you drop the sign. So one of the methods they chose was to square all these voltages. So if you square a positive voltage, it comes up and gives you a positive. If you square a negative number, it comes up and gives you a positive. You'll understand that. Then what you do is you take the average of the square. Another name, so we square a large number of voltages. Everybody says infinite number, right? But they're equally spaced around this waveform. Then what we do is we take the average, which we call the mean. But still it's not right, and then we take the square root of the answer. And what this does is it gives us the effective voltage. So this became known as root mean square. It's the square root of the average of the squares. Root mean square. And we refer to this as what? RMS. Root mean square. It's the root of the means of the square. So it's the square root of the average of all these squares, right? You understand that? And this is RMS. So when I put my meter on AC, what is it measuring? It's measuring the effective voltage. So this 118 volts is not peak voltage. It's not peak to peak voltage. This is the RMS voltage that this waveform represents, which is about 370 volts peak to peak. So peak to peak voltage is maximum peak and negative peak, right? You understand that? And it's going to be a big number, but I don't get the work. And we go to zero 2 times a cycle. How much work do we get when we got 0 volts? We get none. So this voltage is an effective voltage. So it means this right here, if I put 112.7 volts DC across a resistor, this power plug would give me the exact same wattage, the exact same work. It's called the RMS or root mean square. So when you put your meter on AC, it's not measuring peak, it's not measuring DC effective voltage, it's measuring RMS. And so if we say 120 volts, if we say 120 volts AC, it's assumed you're talking about RMS. Because the meters don't measure peak, they don't measure peak to peak, they measure RMS. Now, if it's a sine wave, then this will always be, RMS will always be equal to V peak times 0.707. Or roughly, it's actually the reciprocal square root of 2, which is a huge number. So 70.7% of V peak. It will always equal that if it's a sine wave. So most of your digital meters, your cheaper meters, we call it, they use this value right here. They use 0.707. So as long as you're measuring sine waves, these meters right here are perfectly accurate. If you measure AC waveforms that are not sine waves, then these meters right here are going to measure wrong value. So we have meters called true RMS meters. Have y'all heard of those? Cost a lot of money. But they literally calculate the root mean square. So they have a microprocessor, they have a computer inside of it. But they cost a lot of money. You don't need that unless you unless you're in a field where you measure non-sinusoidal waveforms, like variable frequency drives, variable frequency drives that run AC motors. Those generate non-sinusoidal waveforms. So this guy here would measure something, but it wouldn't be accurate, right? You understand that? So if you're not working in some type of field like that, and you go out and buy a true RMS meter, and here I've got this meter right here, they're going to measure basically the same thing. I got my meter for $80. You paid $300 for your meter. And they measure the same on AC. So true RMS meters are nice. We had a bunch of guys from US Steel, and guess what they bought them out there? Fluke. Fluke is the Cadillac of meters. And they bought them true RMS meters, probably paid $600 for those meters. The meters we do our certification on, those are true RMS meters, but they cost about $400. A good meter that will work you in electronics all the time, you can get that for less than $100. So it's up to you. It's like buying a car that has the ability to go 200 miles an hour and never drive it over 70. So 0.707, this is wrong too. VRMS would equal the V peak. This is actually VRMS is equal V peak to peak. I need to make that correction. So you got these two numbers floating around in your head. So VRMS would be equal to what? No, that's right. This is wrong. Oh, I'm sorry. I didn't see my formula. I made a mistake. So VRMS, you could take V peak and divide it by 1.414. Or you take V peak and multiply it by 0.707. So anytime we take the reciprocal of a number, we get the opposite of it. It would turn a multiplication problem into a division problem. So what I recommend is everything we do, if you remember 0.707, just stay away from that 1.414. This will really help you. Because we're going to get a bunch of numbers floating around. 1.414, 2.82. A lot of books teach 1.414. A lot of books teach 2.82. So I could take peak to peak and divide it by 2.82, and that would give me VRMS. But it would be easier for me to take V peak to peak and divide it by 2 and multiply it by 0.707. I would get the same answer, right? You understand what we're saying? So my scope measures V peak to peak. And we're going to use a scope a lot. Now, what advantage does a scope have over a meter? It shows you what's there. It's a visual representation of exactly what's there. So an oscilloscope measures peak to peak. But if I wanted to know the RMS value, what does your meter measure? Well, your meter measures RMS. So if I need to go between these two testing pieces of test equipment, which we're going to have to do, right? You understand? Then we need to understand how I can go from peak to peak to RMS. Well, we got two options. I could take V peak to peak, and then I could divide V peak to peak by 2.82, and then this would give me the RMS. But now I've got another number in my head, right? You understand? So now I've got three numbers. Okay, I could take V peak and I could divide it by 1.414. I could take V peak to peak and I could divide it by 2.82, right? You understand? Or I could take V peak to peak and multiply it by 1/2 of 0.707. I don't have that number in my head. And then I would come up and get RMS. But if I know this number right there, that's all I need. 0.707. Because now if I measure peak to peak and it's 120 volts, peak to peak, well then what's it going to be? What's peak going to be? Well, it's going to be 60 volts. I can do that in my head. And then I can take that and multiply it by 0.707, and that would give me the RMS value. Y'all understand that? That makes sense. So instead of trying to get all these numbers that these books teaches, you can get all your answers by 0.707. Just remember that number. The reciprocal is square root of 2. Half a peak. Yeah, if you want to go. So which is bigger, RMS or peak? Which is greater? People get that confused all the time. What's bigger? So RMS it's not an average, but it's basically an average. So if I've got a bunch of numbers, is the average going to be the biggest number? No, it's like Mount Everest. So I look at that. What's the average sides of all the mountains in the Himalayas? That would be RMS, the average side. Mount Everest would be the what? would be the peak. So peak is always greater. It's the peak, right? When we say the peak, we mean it's the top. So peak is always greater than RMS. Always greater than RMS. RMS is always less. So I've got 0.707. So let's say I've got RMS, 120 volts RMS. What would it be equal? What would it look like on my oscilloscope? Well, first thing I'm gonna have to do is I'm gonna have to convert RMS to peak. So what would I do? 0.707. Would I multiply by 0.707 or would I divide by 0.707? Huh? If I multiply by a fraction, I come up with a smaller number. If I divide by a fraction, I come up with a bigger number. If you divide by 0.5, you double the number. If you multiply by 0.5, you half the number. So I'm going to V peak. Is V peak bigger than RMS or is it less? It's peak. So, okay, if I want to go to V peak, I'm going to take 120 volts and I'm going to divide it by 0.707. I want a bigger number, right? You understand? That makes sense. What would that come up and give me? By the way, what voltage do you have at your house? Well, we have all types of voltages, you know. So what does National Electrical Code say? They have what they call the nominal or they call it the nominal voltage. So they use 120 volts. So we use 120 volts a lot. Even though odds are it could be anything. It could actually be plus or minus 10%. So you could have 90 volts at your house and it would still be legal, right? You understand that? Normally your voltage is anywhere between maybe 110, 109 up to 100, maybe 120, 120 something volts. We'll use 120. Okay. So what would this give me? Yeah, 169 point what? 73 volts. Or 170 volts. So what would peak to peak be? Well, this is peak. So that means about 340 volts. So Alabama Power is generating 340 volts peak to peak to get 120 volts worth of work. Now it seems like a waste, but it's not, because we can get any voltage we want to with transformers, right? You understand that? And what we can do with AC that we can't do with DC is we can change the voltage level with what? With a transformer. What advantage does high voltage have over low voltage? What is Alabama Power trying to give you? What do they sell you? Power. Well, they're trying to get power to your house, right? Everybody understand that? Well, if I got power, but when I push current through a resistor, what happens? We get voltage drop. Everybody understand that? Every wire conductor has voltage drop because every conductor has resistance. It might be rated at ohms per 1,000 feet, but it still has ohms. And if you push current through ohms, you get a voltage drop. Okay. But Alabama Power is trying to sell you what? Power. So if I've got the power formula, power is equal to V times I. That's the power formula, right? If we transpose that, then I is equal to P over V. What's Alabama Power selling you? What's Alabama Power sell you? What does Alabama Power sell you? Power. So if they can deliver that power at a real high voltage, then what happens to current? The bottom under here, here's the bottom. So if I take 10 and divide it by 2, I get an answer. If I take 10 and divide it by 5, what's my answer going to do? Is it going to go up or is it going to go down? So the bigger the bottom number, the less this on the other side goes down, right? You understand that? So if I can raise that voltage up, what happens to the current to sell you that power? It goes down. If it goes down, what happens to the voltage loss in my wires? V is equal to I times R, right? A wire has a certain amount of resistance. I know it's almost time to go, guys. A wire has a certain amount of resistance per length, right? You understand that? If I can get that voltage up extremely high, then my line loss goes down. So what does Alabama Power do when they transmit that power? They step their voltage up what? Real high. Why do they step it up real high? Less current. Less current means I have less line loss in my wire.
Well, is that the reason why power is kind of goes in one time to
No, the power bill don't go up in the wintertime. The power goes up depending on what appliances you run at your house. So this is why your gas bill, if you got gas heat, is real. You pay a real small gas bill in the summertime, and you pay a real high gas bill in the wintertime. Not because you're using more power. So in summertime, usually your power bill goes up and your gas bill goes down. And in the wintertime, usually your gas bill goes up and your power bill goes down, right? You understand that? Everybody okay? But why do they transmit that? What advantage does low voltage have? Huh? Not really. Yeah, if I'm delivering power, when I start lowering that voltage down, the current has to go up to deliver that power, right? You understand? So what advantage does low voltage have over high voltage? Say it out loud. It's safer. So I can't bring 100,000 volts in my house. I can transmit it on power lines that's, 100 feet in the air. But I can't bring 273,000 volts into my house. Because the closer I get to ground, we're going to start arcing, right? You understand? So what can we do with transformers? Transformers don't change power. Technically, if I turn on a 100-watt light bulb up here, Alabama Power gives me 100 watts. But they don't have to give it to me at the same voltage, right? You understand? So what can they do for transmission? They can step the voltage what? Way up to transmit it, and then we step it down for what? Starts with an S. Take for it. Step it down for safety. So this is why your outlets, your high wattage devices run off 240. Your low wattage devices run off 115. Is it cheaper to run the high voltage devices than it is the low voltage? No, because you're paying for power. But the load is designed around 240 and the loads are designed around 120, right? You understand that? See y'all Tuesday, Thursday. So that's the advantage of AC. We can do what to it? We can step it up for what? Transmission, and we can do what? Step it down for safety. But it does cause those problems. So there are some extremely high voltage DC transmission lines now. Yeah. I'll see you tomorrow, right, Brandon? I know. Now that class starts at a weird time, starting at 8:30.